All right, let's now go over the part 2 of lecture 17. Let's start with a review problem. And this is the time where you should pause the video and try to solve this on your own. Okay. This question has 3 parts. You have a briefcase and it has a lock. And it's an ordered 3 digits combination lock. The first question is how many combinations have no repeated digits? The second question is how many combinations have the digits 8 appear exactly twice? The last one is how many combinations use the digit 0 at least once. So this is more of a counting problem, not a probability problem. So let's look at the first part. How many combinations have no repeated digits? So imagine I have a lock, right? It has 3 digits. And each of the digits goes from 0 to 9. If I'm thinking about having no repeated digits, what does that mean? That means for the first location, I have 10 choices. Since I don't want repetition, after I choose one of those numbers, the second location have only 9 choices. And of course, the third location only have 8 choices because you don't want any repetition. So total, you have 10 times 9 times 8 number of combinations. Another way to write this is choose the permutation of 10 choose 3. And that's 10 factorial over 10 minus 3 factorial, which is again 10 times 9 times 8, which is 720. Okay, that's the first question. Now, with the same combination lock, we're asking how many combinations have the digit 8 appearing exactly twice, okay? So we can break down this into 2-step process. Step number 1 is we're going to choose 2 locations for the number 8. So there is 3 locations. I choose 2 of them. The second, well, in this case, order doesn't matter. That's why it's C, not P. Now the second step is to fill the 1 location left with 0, 1, 2, 3, 4, 5, 6, 7, and 9. So how many choices do I have? I have a total of 9 choices. So now combined, the first step, I choose 2 locations. The second step, to put 8 in there. And then the second step, I choose the remaining 9 numbers. That's the total number. Okay. Now let's ask the last question. How many combinations use the digits 0 at least once? So if you think about at least once, what are the cases? So version number 1 is you say, well, 0 occurs once, or 0 occurs twice, or 0 occurs 3 times. Okay, but this might be complicated. But remember, there's sometimes an easier solution, which is version number 2, is to use the rule of complement. Okay, so what is a complement? The complement is there's no 0 at all in the combination. Okay, so what do I have? So if I choose there's no 0 at all, then I only have 9 choices because I only choose between 1 and 9. And again, in this case, order doesn't matter. So we use C of 9, choose 3 out of 9. That is the situation where there's no 0 at all. But total, we are going to look at all the possible successful event, right? So what is a possible successful event is you have, for the first location, I have 10 choice, second location I have 10 choice, third I have 10 choice. So all possible, I have 10 to the power of 3, and I minus the situation where no 0 occur, then I get the number of combination using digits 0 at least once. And if you play with this number, oh, hold on a minute. We have to be careful. I think I made a mistake here. When actually this is a typical mistake, so I'm going to use this here since I'm solving this live. Where did I make the mistake? Okay. When I say C of 9 over 3, I also added additional thing where all digits are distinct. But that is not the case, okay? In fact, what I have is if I'm only looking at no 0 at all, each location, I have 9 choices. So the correct answer is 10 to the power of 3, which is all possible combinations, minus 9 to the power of 3, because each of the location have 9 choices, excluding 0. So this is 271, okay? So what I have made a mistake is a common mistake for this problem, where I added this red condition, which is not part of the original problem. Okay. All right. So that's that. Okay. So now let's review what is the probability of specific event happens, right? Recall the things we learned in the part 1 of lecture 17 is a probability of an event happening, or a successful event is the size of successful outcome over the size of the space of sample space. Okay. So the top is a space of successful events. The bottom is the sample space, the size of the sample space. Okay, so in more accurately, E is a space of successful events. S is a space of sample space. All right, so now we are going back to look at one of the questions we might have seen before, right? And this is actually reviewed in part 1 of the lecture, of lecture 17. But my goal here is for you to quickly review the solution without looking at, the next slide. So you should, again, pause the video and try to solve this problem on your own. Again, your rule of thumb is to use the formula that probability of a successful event is a size of the sample, size of the space of successful event over the size of the sample space. Okay. And again, to just give you a hint, the solution for the first one is 3 over 36, which is 1 over 12. The solution for the second one is 52 times 3 over 52 times 51, which is 3 over 51. Okay. If you don't remember how to solve this problem, please watch the video from lecture 17, part 1. So now the next question . Oh, yeah, this is just space for you to solve those two problems. Now let's look at the next question. Suppose that you have two dice, one is red and one is green, and both are rolled. What is the probability of exactly one of the die is a 6? And what is the probability that the sum of the die is exactly 5? And what is the probability that the value on two dice are different? So again, please pause the video and try to solve this on your own. Okay, so let's do this together. The first one is exactly one of the die is 6. So remember we said one is a red die and one is a green die. So I have a red die and I have a green die. Okay. So exactly one of the die is 6. There's two cases. Case number 1 is a red die is 6. Green is not. The second case is green die is 6 and red is not. Okay. When a red die is a 6, well, it's a 6, so there's only one choice. Green is not, so you only have 5 choices. So it's 1 times 5. Similarly, when green die is 6, it has one choice, it chooses 6. Red is not, it has 5 choices. So the number of successful event is 5 plus 5, which is equal to 10. And then the number of the sample space, right? You roll 2 die. The first one has 6 choices, second one has six choices, is 36. So the probability of the successful event is n of e over n of s, which is 10 over 36, which is 5 over 18. Now let's look at the second problem. It said the sum has to be 5. So what is the case? Again, the first one, I have a red die and a green die. So what are the possibilities? Let's say the red comes first, the green comes second. The red is 4, so 1, green is 4, right? So this is red, this is green. Or the red is 4, green is 1. Or the red is 2, green is 3. Or the red is 3, green is 2. So those are all 4 cases. So again, my probability of the event is the size of the successful event over the size of the sample space. Size of sample space is always 36. You have 4 possible successful outcomes. That's 1 over 9. Okay. Next one, what is the probability that the value on 2 dice are different? Okay. So in this case, since I have a red die and a green die, so the order does matter. So we're actually using the permutation formula. So in this case, I want them to have a different value. So I have 6 possible values. I choose 2 of them. I assign those values to red and green die, respectively. And the order does matter. So that is permutation of among 6 objects, choose 2 among 6 objects. Okay. So that is, of course, 6 factorial over 6 minus 2 factorial, which is 6 times 5, which is 30. And this is equal to the number of successful events. Now the probability of the event where the value on 2 dice are different is n of e over n of s is 30 over 36, which is 5 over 6. Okay. Right? Now we have the next practice problem. I have Jessica and John. Each one of them roll a 6-sided die. Again, please pause the video and try to solve this on your own. The first one is, what is the probability that John's roll is higher than Jessica's roll? Well, if I want to compute probability, I want to compute again. Oh, sorry. I want to look at probability of event is n of e over n of s. So I need to, again, my focus of solving this is looking at this formula, okay? So let's look at this 2 questions separately. What is the probability of John's row higher than Jessica's? I can enumerate this, but let's first look at what is the size of my sample space. They each have a 6-sided die, and each die has 6 choices. So total is 6 times 6. So there's 36 possible thing. So what is 36 possible thing means Jessica choose among 6 numbers, John choose among 6 numbers. Now the event is in fact looking at where John's number is higher than Jessica's. Let's say Jessica is the first row, and let's say Jessica is the first and John is the second. So what the case is where John has a higher number. I can enumerate them. So it's like 1, 2. So Jessica gave a 1, John gave a 2, Jessica gave a 2, John gave 3, and Jessica gives 3, John gave 4, and 4, 5, and 5, 6. Those are all possibilities. And of course, if I look at column-wise enumeration, if Jessica is a 1, John can choose 2, 3, 4, 5, and 6. If Jessica is 2, John can choose 3, 4, 5, 6. If Jessica is 3, John can choose 4, 5, 6. Similarly, and so on. So total, there is 5 plus 4 plus 2 plus 1, or 1 plus 2 plus 3 plus 4 plus 5, which is 15. Okay, so the probability of the event E is n of E over n of S, which is 15 over 36, which is 5 over 12, if I simplify. Okay, now if Jessica has an 8-sided die, so Jessica now can choose number between 1 until 8. And John is still having a 6-sided die, so he can choose between 1 and 6. So now the first question is, what is a sample space? The sample space, Jessica has 8 choice, John has 6 choice. We have 48 total possible combinations. And now we're asking, what is the probability that John is higher than Jessica? So it turns out, in this case, if I enumerate all possible cases, it's still 15. Because if Jessica chooses a number 7, there's no number John can choose that is higher. So the enumeration is exactly as before. So the number of successes is actually 15 still. So now my probability of my event is n of E over n of S, which is 15 over 48, which is 5 over 16. So compared to 5 over 16 versus 5 over 12, the probability actually decreases because my size of my sample space increases when Jessica has a die of 8 sides. Okay. So again, now this question is something has showed up in part 1. Again, we're putting it here so that you can practice. So please pause the video and try to solve this on your own. And if you can't solve it, try to get back to part 1 of lecture 17. Okay, and here's a hint. What is the probability of value? What is the probability that a value will come up more than once? You can think about what is the probability of a value that never comes up, okay? So that's something you can think about. So in this case, you can use the rule of complement as one way. And also you can use essentially what I would call case study, where a value comes up, more than once. That means it comes either 2 times or 3 times. So those are the cases. Of course, for this particular example, it's most likely that if you use the rule of complement, you might have a simpler formulation. So what are the three rules? There's a rule of complement, there's a rule of sum, and there's a rule of product. Okay, so just a quick review of the rule of complement. The probability of event is 1 minus probability of its complement. The rule of sum, if you have two events that's mutually exclusive, the probability of one event or the other event happening is those probability add together. And then the rule of product is that if you have independent events, so here the conditions E1 and E2 are independent, that means the occurrence of one event does not influence the occurrence of another event, right? Again, Netflix put on a new movie versus today's Sunday, versus today's Sunny does not have independent events. Okay. And that's it for part 2 of lecture 17. And I will see you in the next recitation.